This is a relatively short lesson on a topic called Lagrange multipliers. The central question we're trying to answer is, again, as in the previous section, how to minimize or maximize a function, but now we introduce a little twist in that we require that those functions be maximized subject to a constraint. The easiest way to explain this is to give you an example. So suppose that you run a fast food restaurant chain and you're trying to come up with the best possible hamburger that you can produce for less than $1. And this is important because your competitors sell their burgers for a couple dollars and you need to do the same. And so if you spent more than $1 producing it, then you wouldn't make much money. So you might imagine playing around with different recipes and measuring how good the burger tastes. And you could construct a function to describe this. So you could construct a function whose independent variables are things like the bun, the meat, the cheese, and the different ingredients, or perhaps some measure of the quality of each of these ingredients. And that gives you kind of a recipe, and then you measure the flavor of the resulting product. And your goal would then be to maximize this function. However, of course, you could build an amazing burger if you were allowed to spend $20 making it, but that would bankrupt your company. So you impose the additional constraint that some other function of the bun, the meat, the cheese, and so on, which gives you the cost of producing that burger, must be equal to 1. So we try to maximize the value of the flavor function f subject to the constraint that the cost function g equals 1. So that's an example of the kind of problem that we're trying to solve, what it means to say to be subject to a constraint. Now let's draw a picture that will help us home in on what the correct equations are to answer this kind of question. So I'll draw a picture just in 2D. To represent the function f, I will draw level curves of f, and to represent the constraint g of x and y equals c, I'll just draw a curve. So here's the curve, which represents the constraint, and here are the level curves of the function f that I'm trying to maximize. Blue being the smallest value of f, and red being the largest value of f, and the gradient pointing from blue to red. Now, another way to think about this function when I've drawn this picture is to appeal to our example of the topographical map. And in that context, we would be saying, where is the maximum height achieved by a hiker as the hiker moves along a trail given by g of x and y equals c? Of course, there are many different heights on this page, but we're interested mostly in the maximum achieved only by staying on the trail. And that limits me and gives us a concrete example of this constraint. And if I imagine walking along this trail, say, in this direction, then there's a region in which I'm crossing level curves. And as long as I'm crossing level curves of f, then I'm not yet to a maximum. But it looks like I reach a maximum value of f right at this point on the curve. And at this point, if I can sketch it, we have the situation that the curve is parallel to the level curves of f. And that must be the point of tangency. And so this turns out to be, the maximum point. So this condition turns out to be what tells us that we've reached a possible extreme value. This becomes the new critical point condition for a problem with constraints, that the level curves be tangent to one another. The level curves be tangent to the constraint curve. So let's work out the logic here that leads to an equation. Okay, so the logic starts by saying if I'm still increasing, if I'm crossing level curves of f as I move along g equals c, then I'm still increasing. A maximum, as we just said, occurs when my constraint curve is parallel to a level curve of f. All right? But the constraint g equals c is nothing more than a level curve of g. So a maximum must occur, or a minimum, when the level curves of f and g are parallel. But another way to say that the level curves are parallel is to say that the gradients are parallel, because the gradients are perpendicular to the level curves, and so if the gradients are parallel, then so are the level curves. So it turns out that the definition of a critical point in a constraint optimization problem is that the gradients be parallel to one another. And we represent that in this way by saying that the gradient of f is some unknown multiple lambda times the gradient of g, Remember that the gradients are vectors, and multiplication by a scalar simply lengthens or shortens a vector without changing the direction. So this statement right here says that the vectors, the gradients, are parallel. This unknown quantity right here, lambda, is called the Lagrange multiplier. And it's something that we need to solve for as a part of the mathematical process. I just want to note that if this is, say, 3D, then the gradient is three-dimensional. So this is 3 equations, and this is one extra equation that we have to be on the constraint curve. And so we have 4 unknowns, but of course we have, or sorry, 4 equations, but of course we have 4 unknowns, x, y, and z, and also the unknown lambda, which gets solved for. And this is true in any number of dimensions, that these set of equations represent d plus 1 equations for d plus 1 unknowns, if d is the number of dimensions in the problem. So let's move on to an example. I suppose I should say before we do that, why don't you go back and think about this picture a little bit and what it means for the level curves to be parallel until you sort of understand that pretty well where this equation comes from. The math in this section is not really very hard. It's the conceptual understanding that is worth spending a couple minutes on. So, an example. Here is some function f. In this example, f of x and y equals x and y. And it's subject to a constraint that 4x squared plus y squared equals 4. That can be thought of as saying that the function g of x and y could be written 4x squared plus y squared, and it is constrained to take the value 4. So this is some function right here, and we'll plot that in a minute and see what it is. This constraint here we should recognize as being part of an ellipse. And so if we now visualize that for a moment, here is a surface plot of the function. We see that it is generating some sort of saddle structure. And then here superimposed on that is the ellipse itself. And so we're forced to stay on this ellipse and find the largest and smallest values of the surface plot function, f. And it looks like there'll be maybe 2. If we kind of look at it from the side, we can see that it kind of dips down into the bottom part of the saddle, but also goes up a little bit into the high part of the saddle. And so it looks like there should be a maximum value, perhaps here, and a minimum value, perhaps here and here. So we might expect to find 4 extreme values of this function. To the math. Gradient of f, easy to calculate. It's just y comma x. The gradient of g is also pretty easy, 8x comma 2y. So we then set our equations. Grad f equals lambda grad g gives us 2 equations. Y equals lambda times 8x, and x equals lambda times 2y. And finally, we have the constraint equation itself, that 4x squared plus y squared equals 4. So here are our 3 equations, and we have the 3 unknowns, x, y, and lambda, and we'll solve for all of those. So the solution process is just kind of work through these and solve them one by one. So we start with equation 1. Equation 1 tells us that y equals 8x lambda. Okay? So then we move to equation 2, and we can substitute y in for 8x lambda in for y. That gives us that x equals 2 lambda times 8x lambda, and we can collect everything on one side and see that 0 equals x times 16 lambda squared minus 1. And so lambda is plus or minus a quarter. Okay, so we found lambda. Then we take what we know about y, that y can be written this way, and lambda has one of these values, and plug all of that into the final constraint equation. We get 4 equal to 4x squared plus 8x lambda squared, but lambda is plus or minus a quarter, so 8 times plus or minus a quarter is plus or minus 2, and this all squared becomes 4x squared. So that's 2x squared equal to 1, which gives us x equals plus or minus 1 over the square root of 2. But then y is 8 times plus or minus a quarter, that's plus or minus 2 times x. And so when we multiply x by plus or minus 2, we get plus or minus square root of 2. So we have now found all 3 of our unknowns. Lambda, which is not particularly of interest to us, it was just something that we needed to find along with finding x and y. Plus we have x and we have y. And that gives us our 4 critical points. x can be plus or minus 1 over root 2, and y can be plus or minus root 2. So we take each of those 4 points, 3, 4, we plug in to the function f, which is equal to xy, so we just multiply them together. And all of those critical values have values of f either equal to 1 or negative 1. And so the 1s are maxima, and the minus 1s are minima. Let's go back just one more time to our graph to see if that lines up with our expectations. That looks about right, that there should be 4. They should be roughly symmetric. And so if I now plot a contour plot of my function f equals xy, and I plot my ellipse, we can see that there are indeed these 4 points where I run into the level curves of f, and these are indeed, although it's not shown, these are indeed the level curve f equals 1, which is here and here, and the level curves f equals negative 1, which are here and here. So that all works out. This can be done in any number of dimensions. If we have a higher number of dimensions, we will no longer have level curves of f and constraint curves. We will have level surfaces of f and constraint surfaces, or in even higher dimensions, you could call them level hypersurfaces and constraint hypersurfaces. But we don't need to concern ourselves too much about that. Let's just do an example in 3D to show that the math is really exactly the same. So here's another example. Here's a function that we're trying to minimize, 4x squared plus y squared plus 5z squared. We should be able to look at that and recognize those, that the level curves of this function, setting all of that equal to a constant, will give us ellipsoids. They're all centered at the point 0, 0, 0, and the farther away I get from 0, 0, 0, the larger the value of this function f will be. Then I have a constraint that I'm not only trying to find a minimum value of this function, which would be at the origin, but I need to find the minimum value that also occurs on the plane g of x, y, and z is 2x plus 3y plus 4z equal to 12. So this is a two-dimensional surface. It's a level surface, and these are level surfaces of f. Let's just do a little sketch. I know we can't sketch in 3D, but we can sketch in 1D to give us some intuition about what kind of solution to expect. Here are the ellipsoids as they are achieving higher and higher values as we get farther away from the origin. And here's a one-dimensional version of a plane that sort of passes some point near the origin. And we can expect that there will be some level ellipsoid of the function f, which is just tangent to the plane, and the value on that ellipsoid will be the minimum value of the function. The farther I go away from that point of tangency, the larger will be the value of f, and so I should expect to find one extreme value, and that it should be, in fact, a global minimum. So, again, to the math. It's pretty straightforward, even easier this time. The gradient of f is just 8x, 2y, 10z, and the gradient of g is just 2, 3, 4. So setting grad f equal to lambda grad g gives us 3 equations. X, y, and z all depend on lambda. It's a very nice, simple structure. 8x is 2 lambda, 2y, 3 lambda, and 10z is 4 lambda. So we can solve for x, y, and z all in terms of lambda. That leaves one equation, the equation for the plane itself, and we can plug these values of x, y, and z into that equation for the plane to get this equation here, which allows us to solve for lambda. So we can collect all these things times lambda equals 12, and we can evaluate this sum of fractions using common denominators. And we find that lambda is 240 over 132. Fortunately, that can be simplified a little bit to 20 over 11. And having found lambda, we can then go back and plug in for x, y, and z using these 3 equations, which give us these 3 points, 5 11ths, 30 11ths, and 8 11ths. So really, we're done. We can go ahead and plug that in, find the value, the minimum value, which gives us the value of 10 plus 10 11ths when you work out all the fractions. And if you plugged in a point anywhere else on that plane, you would indeed find that it had a larger value. So this is indeed a global minimum. So again, the math, not too bad, just finding gradients and then solving algebraic equations. But I would encourage you to go back to the beginning of the video and watch the first page of the notes until you're quite comfortable with the concept. What does it mean to have a constraint Why does the constraint imply that the level curves should be parallel? And why does that mean that I have to set these gradients equal to some unknown multiplier times each other, called the Lagrange multiplier?